In this video, we're going to talk about integration by substitution as it pertains to definite integrals. So adding on to what we talked about with use substitution and change of variables with indefinite integrals, so once it didn't have limits to it, we can apply that same idea. So the same integral function in terms of a composite function is still the same as it was last video, but now we're just adding definite bounds to it, so from a to b. And sometimes it's easier to substitute, the variable u in there, so to take the integral of f of u, and then evaluate the a and b values in terms of that g of x or u of x, I suppose, instead of doing this work and then converting it all back to x and then finding those bounds that way. So let me show you how that works with a couple examples. So let's say that we have this integral here of this function, x times the quantity of x squared plus 1 all cubed, dx from x equals 0 to x equals 1. First thing I'm going to do is identify my u value, so that's going to be my x squared plus 1, and du, so the derivative of u, is going to be 2x times dx, because that's the original variable. And so I notice that, there's an x times dx in this equation, and all I need to do is divide du by 2 to get the variable that I'm going to plug in for x dx, which is du over 2. And of course, f of u is u cubed, in terms of u is x squared plus 1. Now, before I go and plug all these things in, I want you to notice that I rewrote, I kept x squared plus 1 cubed the same, but I rewrote x dx as 1/2 times 2x dx, because the derivative of x squared is 2x, but if I multiply it by 1/2, I end up with my x dx. And so the next thing I'm going to do is I'm going to find my u value when I plug in 0 for x and 1 for x. And so when x equals 0, that's 0 squared plus 1, which is 1, and when x is 1, that's 1 squared plus 1, which is 2. So 1 is going to replace this value, and 2 is going to replace that value in terms of u. And so before I integrate, I'm going to pull this 1/2 out here. I'm going to replace that 0 and that 1 with that 1 and that 2, which I found over here. And then this is u cubed, so that becomes u cubed there. And then times du. So I already pulled the 1/2 out, and that 2x dx, which is up here, is just du. So now I'm going to integrate and see what happens. So what happens when I integrate u cubed is I get u to the 4th over 4, multiply that by 1/2, that becomes 1/8 u to the 4th, and that obviously is going to go from 1 to 2. So I plug in 2 first, and then I plug in 1, I subtract these two quantities, so that ends up with 15 over 8. So let's work through another one that's possibly slightly more complicated. So let's evaluate this integral from x equals 1 to 5 of x divided by the quantity of 2x minus 1 all under the square root dx. So the first thing I'm going to do is I'm going to rewrite this thing as the integral from 1 to 5 of x times the quantity of 1 over the square root of 2x minus 1 dx. And I'm going to make u the square root of 2x minus 1. Because if I just make it 2x minus 1, it actually doesn't get me anywhere, and I can't replace all of my things here. So doing that, I'm going to square both sides, so I just end up with 2x minus 1, which I'll come back to in a moment, because it helps me solve in terms of x. So if I have u squared plus 1, move the 1 over, divide by 2, that gives me a value to plug in for x in terms of u. Great. Got something for this bit and this bit. Now all I need to do is figure out dx. So I decided to take u squared equals 2x minus 1, and I'm going to take the derivative because dx means derivative. So I'm going to take the derivative of this side in respect to u, so that becomes 2u times du. And I'm going to take this side in terms of x, so that becomes 2 times dx, eliminate the 2's, and I see a value for dx is u times du. So I'm going to plug all of this stuff in here, and let's see what happens. So here's what I have. So x becomes u squared plus 1 over 2, which comes from here, and then 1 over u, because right, u is the square root of 2x minus 1, so that's 1 over u, and dx we solved to be u times du. Now the only thing I was missing here was translating this 1 and this 5 in terms of u. So when I plug 5 in here, I end up with 3, and when I plug 1 in here, I end up with 1. So now it's time to simplify and integrate and plug in and figure this out. So 1 over u times u goes away, and I can pull out a 1/2 from here, and all I'm left with is the 1/2 on the outside, the integral from 1 to 3 of u squared plus 1 du. I integrate u squared, that becomes u cubed over 3, and then the plus 1 becomes u over 1. And then I'm going to keep the 1/2 on the outside. You don't have to, you can multiply it in, whatever you want to do. And so when I plug in 3, I get 9 plus 3 for these guys, and when I plug in 1, I get 1/3 plus 1, which, calculated all out, that is equal to 16/3. One last idea here that might help you with integration of more complicated functions is determining whether that function is even or odd. So, a reminder is that an even function is symmetric to the y-axis, and an odd function is symmetric to the origin, which means that you flip over the x and then the y, or the y then the x, but it has to flip over twice. Another way to do this algebraically to check if it's even or odd or neither, and unfortunately if it's neither, you can't really use these rules, but if it's even and you plug in negative x into the function and it returns the same exact function you started with, that's an even function. And if you plug in negative x into a function and it returns the exact negation of the original function, so all the signs change, but all the terms are the same, that's an odd function. So, knowing those two things, an even function, if you go from some negative a value to a positive a value, please note that a is the same, it ends up being 2 times the integral of 0 to a of that function. And for an odd function, same deal, negative a to a from f of x is going to be 0, because it's going to cancel each other out, because odd, origin, symmetry cancels each other out. It's kind of cool. So now let's work out an example of integrating an even or odd function. Now I know the title gives it away that it is an odd function, but I want to show you how you can check. So if you have this whole function here, I'm going to plug in negative x and see what happens. So I'm going to take my f of x, and I'm going to plug in negative x into these 4 places, and the result negates sine, but keeps cosine the same. So, fun fact, cosine and its reciprocal, secant, are even functions, so they're going to return a positive result here. So if you plug in cosine of negative x, that becomes positive cosine of x. And so every other trig function other than cosine and secant are odd, so it negates the function when you plug in a negative x. So this ends up being f of negative x is equal to negative f of x. Therefore, this function is odd, and I can already tell you what this answer is going to be from the last slide. This thing is equal to 0, because the area from negative pi over 2 to positive pi over 2, this is the same area as this is. So a negative plus a positive cancels each other out. That's 0. So that's the beauty of working with an odd function. And integrating from the same negative a to the positive a. It's a little different if it's not the same, but we can still work with it. All right, that's going to do it for this video. Thanks for watching.